So our session will start with the first paper, which will be presented by Aman Vyas. Aman Vyas is currently working as a formal verification engineer at Intel. He is applying formal property verification to different IPs and SOCs since last 2 years. He is working closely with various design teams in harnessing the effectiveness of the formal methods and techniques for high quality functional sign-off. And title for his paper is Retry with Confidence. Use formal property verification to verify link layer retry, LLR, mechanism of compute express link, that is CXL. Welcome, Aman.
So, good afternoon, everyone. I am Aman Vyas, and I have been working at Intel from last 2 years. So, I'm very new to this field, formal verification, but it's really a good field. I'm enjoying quite a lot in this. So, it's very early of my career, but then I got to write a good paper on that. And prior to this, like I've already written one paper in DTTC as well. So, yeah. So, the topic for today's talk would be retry with confidence and use formal property verification to verify link layer retry, mechanism of compute express link. Okay. So the contents for this particular talk would be, I will be introducing like what is formal verification. Then second thing, like why we should use formal verification. Then the next we'll look at what CXL design is and how did we like applied formal on that and which feature kind of we verified in the CXL part of it, right? So the third thing is CXL link layer retry. So this would be a bit of a design overview, what we did in this, what this design talks about. Then what problem we had, like what problem statement was there, and the solutions that we proposed for tackling that problem that we had, right? So that is we have coined this a name, directed formal property verification. So once we like propose this solution and handle out the activities, then we had some implementation bugs that we got. So we'll discuss a bit on that. And after that, we'll see that what good results we obtained from this. So immediately we obtained good results and then long-term results that we obtained in this and then conclusions, right? So, okay, so the first question that comes, what is formal verification? So it's a very well-defined technique of efficient and exhaustive way of verifying the formal design. So this definition you might have read it quite a lot of times. So it's an exhaustive way of verifying the entire design. So because of this technique has been this has proven to be very instrumental in producing a high quality design IPs. So it's able to find out the issues in the design, complex timed interface interaction. And the best advantage that we get is we get the bugs in the very early phase of the development and we do not get respins, right? So if we complete the entire design process and then we get a bug, that becomes quite difficult. So it's a lot of wastage of resources, money as well. So the best thing is we are able to avoid the late stage bug escapes and respins as well. So the applications that we use for presenting, the applications we used formal property verification for. So the feature we used there was the RTL implementation that was done for the link layer retry. And we had some RTL implementation issues that were found that we'll talk in the problems and the solutions that we proposed. And there was a deadlock that was suspected in the CXL feature, so between the host and the device. So that was the main point of concern which was flagged. And we kind of verified this particular feature, LLR. So that is called link layer retry. In a short while, we'll discuss what LLR is and what CXL is. So now, why formal verification? So I have given a couple of points to compare, like how traditional simulation is different from formal verification. So in dynamic simulation, the main problem that is there, or the main challenge, is that we do not cover all the possible cases that might exist. So let's say if there are 10 inputs, then 2 power 10 combinations are possible, out of which, let's say if there are legal scenarios 2 power 8, then we are not covering the entire possible cases. But formal kind of provides us this guarantee that we cover entire possible cases which are possible for that particular design. So dynamic simulation becomes quite expensive in uncovering all those type of control logic flaws, and it's even hard to generate this. So which in turn kind of results to late stage bugs that I discussed in the previous slide. And formal verification, again, it's an exhaustive way of verifying the design. It's breadth first analysis approach that we use over there, and we get to find the early stage bugs. So now a brief description on what CXL is, why it is used, and so I think yesterday we had a good session on CXL 3.0, if people would have attended. So basically nowadays there is a lot amount of data that is, so there is a lot of data that is being generated because of the various applications that are there, like cloud computing or artificial intelligence, machine learning, etc. So yottabytes of data is being generated, right? So there was a kind of a requirement to move to, architectural change in the type of devices right now we have. So like PCIes, or previously we were using PCIes. So to architecturally change or fundamentally change these things, we went for this technique. So we went for this technique of using CXL, that is Compute Express Link, where it's an open industry standards which kind of provides a high-speed interconnect between the host or the CPU to the memory devices. So it kind of maintains the memory coherency between the memory space that we use from the CPU and the memory devices. So this technique, so CXL was like, people were motivated from this because of the large amount of data that gets generated. And previously, like in PCIes or other, they have a dedicated processing space or dedicated processing memory. But rather now in this, intelligently the pooling or concept takes place, where where intelligently have to decide that what amount of resources can be used and it can be shared. So that is the basic overview of what CXL was meant for. So now there is a feature inside that called as LLR, that is link layer retry. So any type of data bus that are there, so if you'll see any type of data bus, they're susceptible to transmission errors that can occur. So there, if let's say for example, if there is a transmission error that happens, then we need to neutralize the effect of it to get back the normal functionality or normal working of the CXL. So for that, there is a mechanism inside the CXL called as link layer retry, where if let's say we have a CRC error that is happening, then in that case, there has to be a recovery mechanism to get out of that CRC error. So basically, we use a technique called as the link layer retry. So this is a bit of a design. I'll talk a bit on that. So CXL specification is an open industry standard, and there are some fixed number of variables that are there inside the CXL specification. So these are some variables that I have given here. So these are standard ones that every CXL design you will find in. So link layer retry buffer. So it's a kind of a buffer that stores the flits, that is retriable flits that are moving from the transmitter to the receiver side. So that is a buffer. Then we have two state machines. So this is not, so this is specification based thing. So the two state machines are LRSM and RRSM. Then there are some other parameters like timeout counter, number of retry counters, and then read-write pointers will make sure that we manage the we manage the LLRB's empty and full kind of a features. The last signal, the second last signal, num-free buff. So num-free buff was the most important variable here, which have a fixed set of rules, I would say. So they have fixed set of rules in the CXL specifications that needs to be followed, and this particular variable tells us how many free LLRB entries are available. So this will be used, the techniques that the solution that I propose. So just to provide a start point. So now this is a flow of a simple LLR sequence of events, which is using one host and one device. So let's say we have a local retry state machine and remote retry state machine. So these were the two state machines. So normal operation is going on, and we get a flit that had a CRC error. So we move to the local RSM, local retry state machine, and then the receiver should make sure that transmit side, the LLR request is generated. Once the request is generated, there are certain, again, some parameters which are there that are frames, sequences, and all those things that needs to be sent to the remote machine to understand like which flit have undergone the CRC error. So once we get that, we wait for the LLR acknowledge to address that the CRC error has occurred, and then we expect a wait to come, so ACT to come. So LLR ACT will tell us that, okay, now the particular CRC error that you received has been completed, has been done, has been removed, and then basically then we move out to the normal state. So this is kind of a basic, simple LLR sequence flow. So normal, then we generate a request, that means error has occurred, then we send out the ACT saying that, okay, the error has been resolved, and then the normal operation is again turned in. So that was the basic overview of the design we handled. So CXL and LLR things. So specifically, we kind of verified the LLR feature. So the main problem which started was this way, that there were the design teams, and they have already, their simulation team have already signed off the design without, with that went ahead to the later stage of the design cycles. So once that was done, when the SOC simulations were going on, there were two critical bugs that were found in the design of CXL. So, I mean, you can think of this in this manner, that already the design had been so matured, and then you get a deadlock kind of a bug, which is seriously a critical bug. How much amount of resources we would have wasted by then. So this basically problem that SOC simulation teams flagged kind of motivated us to do the formal verification on CXL LLR feature, which kind of guarantees, or which kind of tells us with a good confidence that, yeah, we can remove 100% bugs from that. And that's why we started, that's why we took the ownership for this particular problem. So right there you see there is a host, there is a device. So the problem that was expected was, so our deadlock was suspected between the two link layers of the host and the device that could arise because of n number of reasons. But the first major reason that we saw was the LLRB that I discussed. So it had some specification rules, like let's say, take one example where one rule was that LLRB can never be 0. So that rule was being violated when we kind of ran some assertions that I'll discuss. So these type of rules were being violated in the CXL specification, which was leading to kind of a good amount of deadlock scenarios in the link layers of host and device. So the challenge that we had was to first find out all those bugs that are existing in the design, and also to like fix all the potential flaws that might arise because of other such type of variables or other such type of rule violations. So now this we could have handled using traditional FPV techniques, but the traditional FPV techniques, if you'll see, so we had around a host and a device. So in the host, there would be an RTL instance, in the device there would be an RTL instance, and overall scope of the design will become quite large in that case. So the first thing that I said, 2 instances of RTL. So there would have been host and device instances that we would have to be considered if we would have gone through the traditional FPV approach. And then right behind, if you see, there was a transaction layer in the physical layer. So link layer retry mechanism sits inside the link layer of the design. So transaction layer and physical layer will be kind of our outside environment, which we need to model. So good amount of modeling would have required. So detailed set of constraints on input would have been a challenging task for us. And then end-to-end forward progress checks using safety and liveness SVS would have required. But the major thing or the major disadvantage of formal sometimes is that we face a convergence issue most of the time. So forward progress checks become quite difficult to handle till the time we have a good understanding on what abstractions are and what other complex reduction techniques are. And since this was this activity was kind of a high priority task for us because the bugs were found in the SOC simulations, so we kind of thought of another way of handling this particular problem. So we did not went through the traditional FPV. Rather, we proposed the solution of directed FPV. So now what directed FPV is? So this is this is a strategy that, so we did not focus on the complete, I would say, complete test plan, and then, developing checkers end to end, spurious, all those things. Rather, we kind of focused on deadlocks that can stem from retry mechanism. The reasons for the deadlocks that can stem from the retry mechanism. So now, if we would have used, so with this approach, we had two challenges. Number one, so we had to tackle the architectural bugs. So there can be some things that in the architecture itself or in the high specification document itself that might be carrying bug. But this activity was already carried by one of our team members who handled the architectural bugs. So this particular thing was assumed by us that this architectural bugs are nowhere existing in this. So we kind of focused on the implementation bugs that RTL implemented. So in this, we did not target, as I said, on generic SVS. Rather, we focused on going through the specification, understanding that it's complete robust and it's bug-free, and then identify the set of rules that might be there inside the CXL which needs to be validated. So we handled, this important variables that I discussed. So we kind of went through line by line and identified the rules that needs to be implemented as system Verilog assertions, and then to avoid the complete deadlock scenarios that might exist. So this is how our formal environment then looked like. So we avoided using the device part of the CXL. Rather, we used the host, and transaction layer and physical layer was modeled. Small amount of modeling was done in the FPV environment for the transaction layer and physical layer. That too, we started with writing the SVS. So first we went through the document. We kind of identified the rules that were there and coded them and binded them to the link layer part of it. And then when we started getting the counter examples, so we kind of did this activity on the Jasper tool, so Jasper Gold from Cadence. And when we started getting the counter examples or the errors, we came to the conclusion that if it's a problem because of some constraints that needs to be fixed, we kind of added them, and it was a whole sequence of process. So this activity, we split it into 4 parts. So the first one was we extracted the complete set of rules from the CXL specification. Once that was done, so we kind of went through all the alarming part of the design, like where the bugs was hidden, which could be hiding bugs. So we went through them, identified the rules, came up with English list of checkers. So that was the first step that we did. And then the second one is we had some architectural, already in the specification, there were some signals that were present. So we mapped the microarchitectural specification structures and variables that were there in the CXL document with the RTL that was implemented. So once that was done, then we implemented the rules as system Verilog assertions, which were very basic rules that we implemented. And as and when we started to get errors, we added interface constraints for transaction and physical layer. And to our surprise, once this entire thing was fixed, the environment was stabilized. Even after, I've already told that SOC simulation was already done, we found 4 more critical bugs in this CXL implementation. So, and it had gone through so many stages, and after that we got 4 critical stage bugs, which was kind of created, problematic thing for the designers because the implementation was not completely adhering to the rules that were there in the specification. So this I have given a brief example, what type of rules were there in the design specification doc. So let's say there is a entry called as num free buff. So there were 3 rules I can remember of. So the first one was that it can never go to 0. And if it is going to 1, then it should be, let's say, if it should have a ACK that is being returned from the sender to the receiver to the sender side. So such type of rules we came across, and then we came up with the English list of checkers. then again, we identified the blocks and signals in RTL that maps to the specification, which were more or less relevant from the deadlock point of view. So this is how we implemented the system verilog assertions. So let's say when LLRB was less than equal to 2, then at that particular time, and if it's a control flit, then we expect an ACK to come. So initially when we started like debugging this, we used to get results in 5 or 10 minutes. And with this, so we came to know that there were a lot of constraint modeling that was missing. So we started modeling the constraints and all those things. But once this environment was stabilized, these checkers were failing, and there were 4 reasons that came up, which was again hiding in the design itself. So 2 I have discussed in our slides. So and the 4th one was, so let's say there was physical layer and transaction layer modeling that was to be done. So let's say one such constraint was whenever we expect a physical layer valid and no error is there, then number of acts that the physical layer can send to the link layer must be always less than or equal to whatever the acts we have right now. So these type of constraints we fixed, and our system was stabilized. So the first bug that we saw was the num-free buff, which explicitly in the design document, it's mentioned it's an open industry standard. So you can see that it says that LLRBC, this num-free buff can never reach value less than 2. If it reaches, then it should be having always ACK in that. So there is a signal inside that structure which says that ACK should be always applicable. So this rule, I mean, with such a small assertion, we can prove that, and this was failing because there were 2 reasons for that. So when RTL was implemented, it was implemented in the design stage. So there were some features like credit counters and flit packing, all those things were taken into account. So so because of this, there were some pipeline stages in the RTL design, and because of this pipeline stage, there was some back pressuring that was introduced. And to our surprise, it was seen that the calculation of what pipeline designs they have done was a bit wrong, and the RTL was picking up the wrong values of this back pressuring kind of thing. So the first bug was there was a residual retriable flits in the TX pipeline, so which was causing this num-free buff to float as low as 0. So float as low as 0, which was completely an illegal behavior. And I mean, LLRBC equal to 0 means that there would be a deadlock scenario that will hit between the host and the device. And the second type of bug that was found was there is a parameter called as the static check error. So there was a spurious detection of acts that was happening in the RTL. So that was another important feature important bug that they missed somehow, and it was again a completely wrong implementation of the RTL, which again went through the entire design process and was found very late in the SOC simulations. So I mean, this way it tells us right. So we have formal guarantees that we are not leaving any scope of bugs inside when we validate the design with formal. So formal sign-offs are, it more or less says that it's 95 or 100% bug-free. So immediate results. So this, we were able to apply the formal technology on CXL design completely, even only using the host part of it, right? And 4 very critical bugs were found, which skipped quite a lot of stages of verification. Finally, once we formally verified it, we gained a good amount of confidence, where we said that now this design is not having any bugs with respect to deadlocks at least. And the design statistics, so this is, this we can skip. So, and overall results, then seeing such a good results in a very short span of time, it kind of motivated higher managements to allow us to perform this activity on other IPs as well as on other 3 server SOCs. So this particular concept that we used started with just 1 generation design IP, but then we went ahead and used this for 2 more generations of IPs and 3 server SOC designs. So results, timelines, and I have results I have tabulated here. So in the first SOC, it took four engineering weeks because we kind of were missing a lot of amount of constraints. So once that particular things were fixed, that we fixed all the constraints and all, so we reproduced the late stage deadlocks that was identified by the SOC teams. So we kind of verified that. With that verification, we got two new more bugs which was not even found by the SOC teams or the SOC simulation teams. So two more bugs there. Then the process was like the RTL was fixed, and then we got a new RTL. We again checked that, and in the proposed fix also there was another bug that was lying. And one more time it happened. So it was 4 bugs were found in, I mean, just 4 engineering weeks for the first SOC. Once that entire thing was fixed, then we validated and we kind of provided the sign off on this. Then we moved to the SOC B, the second generation SOC of the server. There already, since the environment was more or less set and constraints were properly set, only a small amount of fixes in terms of constraints or small amount of constraint fixes were done. And then again over there in the next generation SOC, we again found 2 new RTL bugs there. Again validated the fix, and then we signed it off. So with this activity going on, that particular design group started focusing, I mean, on formal quite a lot, and they enabled the formal on SOC C as well. Luckily over there we did not get any bug, and so that helped us provide a good amount of confidence that yeah, okay, now we are good to sign it off, and at least from deadlock point of view, we are not hiding any bugs in this design. So conclusion, I mean, this CXL is a very elegant architecture. It's a very good architecture. Since we are like having a lot amount of data and almost all of the companies are moving on this. So to implement such a good elegant architecture, you need to be completely sure that the design doesn't hide any bugs or doesn't have any implementation bugs if you're using. So with this technique that I showed, directed formal property verification, just the 4 steps, and we were able to provide straightforward, quick, robust solution, which and we could have we said it with full confidence that okay, now it is not having any possible scenario that is being left. So that was the type of confidence we got. So yeah, that was the conclusion. And yeah, so future scope, like now there, so this was just one feature for LLR which was there. So there are another multiple features inside CXL. So one such feature is LPIF, Logical Physical Interface, I think you might have heard. And the second one was integrity and data encryption. So we kind of enabled the formal verification. I mean, the design teams got a good amount of confidence on us on like when we were delivering such a good results. So we enabled the formal verification on other features of the CXL as well. So right now, logical physical interface and IDE feature we are validating, and again we are getting a good number of bugs in this. So yeah, that's all.
Thanks a lot, Aman. Thanks for reliving the whole experience of verifying the LLR with formal. And you really took it through all these stages, including debug. Thank you very much. Questions for Aman? Very easy.
Okay, so some of the tools have automatic analysis of the deadlocks and all. So have you tried that on this particular design?
The superlint type of a thing, you see?
Yeah.
Yeah, we did that, but that is that comes with the some limitations, and that is the general trend that we follow. So we every time we start with any design activity, we tend to run the superlints, but then it doesn't assure that it's bug free. So
Okay.
that is quite early in the stage of development, superlint tool. So did not completely relied on it, but to answer your question, yes, we did that.
And this particular deadlock, it was not, the tool was not able to automatically
No,
find
no.
it out. Okay, so that feedback has gone to the EDA vendor so that they can develop our
Yeah, actually
website.
that tool is in a very early stage of development. These guys are fixing that some things, but yeah, it is not today. It's not that mature to completely flag all the types of deadlock issues. Yeah, maybe Kiran can add.
See, formal verification, if you are looking at the automated tools, right? The automated tools are for boys. What we did is for the men.
Maybe just for tool people can answer.
I'm sorry? I said the automated formal tools, what you could do, what you could achieve for that is very limited in the scope. If you are really serious about formal verification, it has to be deeper into the design, and this is how we have to go get into it, right? So if we have to discriminate between boys and men, Superlint is not the tool.
I have one more question. So about directed FPV. So you found this particular bug in simulation, and in your formal environment, you would have constrained or over constrained it to hit it. That's what you mean by directed
So
FPV, right?
by directed, I mean that instead of implementing it completely from end to end and getting trapped into the convergence issues and all those things, we just implemented the basic rules where we expected that the bug was hiding. So we had a meetings with design and design teams.
So consider a situation, I am not doing the simulation, and I started with formal, with basic valid constraints. Have you tried that just to see whether we will be able to hit this particular deadlock, or we are getting into more trouble?
No, so basically SOC simulations were done.
I'm just wondering, I mean, I'm not going to do the simulation. I'm starting with the formal. So with the basic constraints and everything, will this bug be hit or not?
Yeah, definitely it will be hit. So
you have
we
tried
guarantee
that?
100% bug. Even if one is lying, we'll get it. So yeah.
Okay, thanks.
I think that's all we have time for the question answers. Maybe the last one.
So the design seems quite complex based on the number of gates. Did all the properties get proven? Did you use any abstractions?
No abstractions was not required because we were getting good convergence. I told you. So we kind of shred the design. So that design parameters that you saw were for whole RTL. I mean, both the complete transaction physical layer and everything. But we binded the RTL only to that part of the design, link layer part of the design. So we did not get into the convergence issues. And we didn't wanted to get into the convergence issue. That's why we chose this approach, because we had a very short amount of time in which we wanted to reproduce the errors, as well as we wanted to, validate the bug fixes that were coming in, right? So had this been activity where formal would have been started very early in this stage, then we would have carried it through the entire process that you might have heard of in FPV, right? Does that answer your question? Thank you.
Yeah, thanks for your questions. I think that's all the time we have.
Yeah.
Aman is around. I'm sure he will be happy to answer your questions. Offline, you can talk to him. I would like to invite Shrobana to hand over the certificates to all the authors. So if authors, all of you can come up.
Only I am there.
Okay. Kiran is here.
Kiran can.